Hello, in today's video we're going to be taking a look at how we can calculate the area enclosed by a polar graph. But in order to do that, let's remind ourselves about how we already used integration to calculate the area enclosed by the graph of a Cartesian equation. Of course, at its most basic level, you could have something as simple as a rectangle, and if that rectangle had a height of y and a base of x, then the area would of course quite simply be y times by x. But that's quite basic, so we obviously extended that idea and then said, what if the top of the area is not a straight line and is instead represented by a curve? Of course, that curve could then be represented by an equation of y equals a function of x. All we then had to do to work out this new area is, instead of doing y times by x, to take account of the fact that the y value is varying depending on what x value you're at, is do the integral of y with respect to x. But you can still see that structural idea of the y being multiplied by the x in the structure of how we write the integral. We've got that y times by dx, and that's what's being integrated. So, on top of that, it's worth pointing out that as we're integrating x's, you're specifically finding the area between the curve and the x-axis. And then also that means the limits are x values too. But if you have something like x equals a, well, x equals any number is a vertical straight line at that x coordinate. So this tells us how our area is bounded looking from left to right. Our area is going to be bounded by these vertical lines at the points of our limits. So that means our area is going to start at x equals a and go from left to right all the way until we get to our second limit, which then provides the ending of our area at x equals b. So that's how we can use integration to find the area enclosed by Cartesian equations. What happens if we want to find the area enclosed by polar graphs? Well, luckily there's a clue in something we've already looked at before. Because a lot of polar equations are concerned with things that sort of go around the pole rather than just from left to right like a lot of Cartesian equations, therefore we can relate what's going on with polar graphs to circles. If we're just finding the area of a part of a circle, which we call a sector, that is of course just going to be half lots of r squared theta. But that's assuming that r is a constant value, i.e. you've got an actual circle involved. But of course, polar equations are based on this idea that r can be expressed as a function of theta. So all we've got to do is an adjustment similar to what we did before to the formula for the area of a rectangle. All we're going to do to take account of the fact that r is varying with respect to theta is it means we've just got to integrate r squared with respect to theta. And then you still have that half out the front, just like we did in the formula half r squared theta for area of a sector. To get an idea of what area you're finding when you're doing this, instead of viewing it as the area between a curve and an axis, a straight line in other words, view it as the area enclosed by the curve and the pole. Which is a bit weird because you think about the area between a curve and a point, but you'll see exactly how that looks when we start factoring in what our limits are doing. Our limits are theta values. And that's interesting because if you have theta equals a number, the sort of graph that's representing on polar coordinates is still a straight line, but it's specifically a straight line that's always going to go through the origin and is an angle of theta rotated anti-clockwise from the initial line. So if we have a polar graph and then we have a limit of theta equals pi over 24 as the lower limit for integral, that means we're going to have a line that looks something like this. Then instead of the area being formed by going from left to right across the graph, the area is then formed by rotating anti-clockwise from that lower limit theta value all the way around until you get to that bigger theta value limit, which then will enclose the curve with another straight line rotated at that angle. So that's how the area is formed, and these are the sort of shapes you are forming when doing polar integration, where you've got two straight lines at different angles going from the pole to the curve, and then it's all the area in between that. It's worth noting that this formula for the area on a polar graph is actually in the form booklet, although a lot of students do end up just remembering the formula anyway, just because they use it enough and because of its strong relation to area of a sector you've seen before. But beyond that, if you understand how to do integration, then actually applying the formula isn't too bad. But let's take a look at an example anyway. So we have got the graph of r equals 3 plus sine of 5 theta. Fine enough, that was a graph you'd seen on the slide before. And we want to find that area enclosed between the curve and the pole and the lines theta equals pi over 24 and theta equals 5 pi over 6. So how are we going to do it? Well, we've just got to apply that formula we just saw. The area is going to equal half lots of the integral from theta equals pi over 24 as our lower limit, and our upper limit, as we're stopping at 5 pi over 6, that's our upper limit. And then it's going to be the integral of r squared, so that means our equation representing r, so 3 plus sine of 5 theta, all squared, and then we're going to be integrating thetas. So, continuing this question on for completeness, it's worth pointing out we just start off by multiplying at the brackets. Because it's only power of 2, that's not too bad to do. If it was, of course, an integral with a power of 3 or something, that's something where from Maths A level we know already, you should be trying to find a different method. But power of 2, yeah, that's not bad, so we just go ahead and multiply the brackets. So fully multiplying them out, you get something that looks like this. And now we've got to do the integration. But in order to do that, we need to know how to integrate sine squared 5 theta. And a reminder from Maths A level, that requires use of an identity. The identity you need to use is, of course, one of the double angle identities for cos 2 theta. Cos 2 theta is equal to 1 minus 2 sine squared theta. And therefore we can rearrange this to make sine squared theta the subject of the formula. Some students should remember what this rearrangement is off by heart, but I'd argue that's too much effort. It's better just to remember the identity and then just get very quick, even quicker than I'm doing it here, at being able to rearrange it. The reason I'm doing it at this speed is because I'm having to talk at the same time as write. Anyway, worth pointing out, we don't have sine squared of theta. We've got sine squared of 5 theta. But that's not a problem because, as a reminder, of course, you can adjust identities by just doing a substitution inside the trig functions to adjust the variable to whatever it is you want. So if we're replacing the theta with 5 theta in the sine squared, we've got to replace the theta in cos of 2 theta with 5 theta as well. So instead of being 2 lots of theta, it's 2 lots of 5 theta, which would be 10 theta. So therefore, we can now place that into our integral. And that will get us the following. Of course, then once we've done that, we realize that we probably want to gather the half and the 9 together, even though it's going to take more writing out. Bit of a chore, but there you go. And that will get us 19 over 2. Now we can finally go ahead and actually do the integration itself. So keeping the half out the front, I've been writing it every time because if you get lazy and go, oh, I'll remember it later, you rarely do. But anyway, 19 over 2 would integrate to 19 over 2 lots of theta. The sine, watch out, that would integrate to a minus cos of 5 theta, but then there was a 6 in front, but because there's a 5 in front of the theta, we've got to divide by 5. And then minus cos will integrate to minus sine. It was a 10 theta inside, so still a 10 theta inside. But then, because of that 10 in front of the theta inside the trig function, we've got to divide by 10. So 1/2 divided by 10 gets us 1 over 20. And then, of course, we've still got our limits. So the last thing we've got to do to finish the question off is plug those limits in. Now, it's a bit of a chore to do, but it's worth pointing out there's almost always a method mark for showing you understand how limits work on integration questions. So therefore, I'm literally going to rewrite out this expression with the limits plugged in, just because that then shows the examiner I understand how limits work. So therefore, it's going to be 19 over 2 lots of 5 pi over 6 minus 6 over 5 lots of cos of 5 lots of 5 pi over 6 minus 1 over 20, lots of sine of 10, lots of 5 pi over 6. And then doing the same with the other limit obviously making good use of brackets to ensure everything is being applied in the correct manner. And this ensures if you make a silly mistake typing stuff into calculator, you still get all the marks for this stuff. Now it's worth mentioning this question wanted our answer to 2 decimal places, so for this particular question we don't have to worry about putting things in exact form, but do watch out for those questions that do. But therefore, as a result, for this question I can just plug it all into the calculator and see what numerical value I get out of doing that. If I was to do that, I'd get 11.77259 and then some more decimal points, but therefore to 2 decimal places it's just going to be 11.77, and therefore that is our final answer. Okay, that's how you do polar integration. However, there's some more things we could look at in the future, such as how do you find the area enclosed by 2 different polar graphs, or the area between 2 polar graphs, if you will. So that's something we're going to be looking at in a future video. That will do us for today though. See you in a future video. Goodbye.